So I want to ask a question. How many of you are still perfecting your computing network for GPU? Are still working on that? And how many of you want to scale it up to 500,000 of GPU? If you want to do that, right, you are at the right place. We are going to take a different look, how to achieve that. Let's look at the state of the art. So the surge of the performance critical network from LLM, that sort of thing, right? That's what we are at, cloud AI, HPC. And we are in the process of transforming from the information infrastructure to computation infrastructures because of the AI. And we are dealing with several issues, not on the scientific side, but it's on commercializing the technology that we might already have, right? Is the integration of commercial routing and the non-minimal path routing into the performance critical network. And we also have an issue, this will remain incomplete. We also have some issue on integrating these technology into open source solutions, remain incomplete. And these hinder scalability and interoperability with the cloud infrastructures. So let's look at my company. My company is Claruspon Systems, is a technology and commercial company incorporated in California. So we do software, open source space. On top of it, we further develop the routing technology on top of it. We have hardware products, Ethernet and fiber in an X. X represent in a rack or in a box, both of them. And we do services. The services is we help strategic customer on fulfilling and implementing the routing strategy. And we also maintain an ecosystem, like the open source community, the Sonnet community. Our service operation typically works like this. We come in and evaluate. We look at your network, evaluate your switching box, right? And we work with our customers to implement a strategic routings. And then we implement the non-minimal path routing technology into your box. And our customer has a choice of black box or white box. That's our service is about. We have a demo platform in the picture, as you see, is a 5-node mini pod and running non-minimum path routing right now. So let's say you are a serious customer, so you want to engage on the business side, then we are going to let you see and play with this demo platform. And we have additional resource, the blog and the corporate website. You are very welcome to take a look. Now let's define what is minimum path routing. The minimum path routing is a technology that explores a larger topological space when building route tables. Now I want to remind you, okay, even today's BGP is able to see this larger topology space. The current BGP see everything, but it's not doing everything. It's only doing the shortest path first, algorithm. That is what limits its visibility, okay? We have to go beyond that. The minimum path routing exposes additional paths in the network. When you got additional, let's say a lot of these additional paths, right? You got two things. One is, with these additional paths, you statistically reducing the congestion in the network because you have more route to choose to spread into it. And also you got huge amount of additional cross-sectional bandwidth. That's what you need for the computing network. Now, with these, we can solve the problem of building a much larger GPU direct networks. And we can also build computation networks, and we can even interconnect them. Now, having said very large, right, I want to mention, even in a smaller scale network, right, with this nominal path routing technology, it will give you the value, the ROI. As we see, it's also very good in building smaller, let's say, inferencing computing networks. We will see. This will illustrate what's the problem with the current BGP. Okay, let's say the node 1 want to build non-minimum path to reach node 2. In the traditional BGP, what's happening? Node 1 want to reach node 2, but doesn't take the shortest path. Node 1 want to take node 1, node 3, and then node 2. Node 1 want to take node 1, node 4, and then node 2. In order to do this, let's make an attempt to do this, right? We let node 2 advertise its prefix, but we block the prefix from directly going into node 1. So the node 2 prefix will go to node 3 and then node 1. Node 2 will go to node 4 and then node 1. So node 1 learns the non-shortest path route, but the problem happens. Node 3 learns directly from node 2. If you want this network running completely with some control, non-minimum path routing, this breaks. This doesn't give you that, okay. Now, however, if you think this way, if you're chopping the network into slices, if you have 4 nodes, you chop it into 4 different slices. Within each slice, you do the first I mentioned. You treat it as a node 1, okay. All other nodes are advertising, but block the advertising goes through direct path. If you do that in each of the layer for each of the node, then you accomplish something. Let's see the emulation, see what can you accomplish. This is node 1 sending a equal cost path, but it's a non-minimum path. Okay, it goes through 3 and 2, 1, 4, and 2. It furthers. 1 go to 3, how does it look? Yep, it goes to 4, how does it look? And now we are talking about how does 2 send traffic. It looks like this. That's the pattern. That's something you achieve. Yep. Now, when a network is smaller, there's a little bit tax to pay, okay, because you're going to grow the routing table. On the right side, it will grow a little minimum routing table size, right? But that's the tax you have to pay to get this technology in place. But it's not that much, okay. For smaller layer network, you can hold the entire thing in your routing table. Therefore, you have a choice to make underlay the same as overlay. But for larger layer network, you want to build, let's say, build 256 node network doing these kind of behavior. You want to separate the underneath layer, underlay layer, from the above layer, okay. Tunneling will be needed to conserve the routing table. And we are pretty close to support VXLAN overlay encapsulation technology. How come? Okay. This slide shows what is the other use of this non-minimum path routing. Let's see how it accomplishes traffic engineering from a carrier network. This particular carrier network tries to send 3 different types of traffic through 3 different types of network paths between node 1 and node 3. Okay. In this slice network, within each slice, you are using traditional BGP's shortest first path algorithm to build it because you can, because you already slice it. Now, the way you slice it, you can call it is a strategic routing. You first define it first. And to solve the same problem, you just slice it into 3 layers, okay? And then at each slice, it just runs the traditional BGP. So you can accomplish the same thing. Now, you want to ask, why do I want to go for non-minimum routing, right? Now, starting from this slide, we're going to build some terminology, and the subsequent slides will tell you the whole story, why we want to go non-minimum path routing. Besides just, you already know, it will unveil a lot of paths, right? But how? In what way? Route path refers to the path traversal from point A to point B. It's that simple. That's the simple. Now, let's first take a look at the Clos technology, the Clos topology, okay. From point 1, the tar point of view, when they want to reach 2, 3, 4, at this column give you the route path, the view of route path, okay. Because it tells you how many paths actually can be routed from node 1 to node 2, node 3, node 4. That's what we call the route path. And we look at the mesh. We look at the mesh to say, oh, I want to do the similar stuff, right? I want to explore, even though it doesn't look like there are many paths, but from packet point of view, right? It really goes through following your routing table. Let's build a routing table in a way that we previously mentioned, taking the not shortest path, and you build a route path for this particular mesh, right? It will look like this. Can you see the similarity? Now, if you think deeper and observe deeper, right, you will find out the class, the route path, and the topology are the one entity, are the one thing. It doesn't have flexibility. The route paths in the class are restricted by the topology. And in the mesh, in the different kind of topology, right, it's your routing strategy defines what the route paths look. That gives you the extra flexibility. Can you see that? That's why we say a route path is ultimately determined by the routing table, not the look of the network. That's something I didn't hear before I doing this kind of research. And therefore, we say we have 2 bullets, right? Class as related route path. The route path is determined by the topology. And mesh as related to its route path is determined by you, the customer, based on your business objective, define the route path with extra level of flexibility of control. Now, as we know on the internet and the data center, right, we are using TCP, IP. So it has flow, concept of flow and subflow, or even packet. Now, you will get a lot in data center, you will get a lot of flows or subflows, a lot of them. But you are mapping into a limited number of paths. That's the problem. The mapping wraps many flows onto a fewer route path. Remember, it's route path. Therefore, create condition for traffic collision. Now, what if you have so many paths with that choice to go with? Then the condition diminishing statistically as the number of route paths increase quadratically. I use quadratic is because this Dragonfly, right, gives you that quadratically growth rate as far as number of paths, route paths, and even the cross-sectional bandwidth, same thing. Now, we understand what route path is. We have to understand what is maximum number of non-overlap route path is. This is a route path. The black one is a route path, right? The other is also route path. As long as they don't overlap, means they are not making exit from the same spine switch, right? As the picture shows, they are not overlapping. So in this topology, in this configuration, right, the number of non-overlap, the maximum number of non-overlap route paths is PM divided by 2. That's the number of it, the maximum possible number of it. You go back and do the math, you will better understand this. And for the bottom, the mesh, right, the maximum number of non-overlap route paths is another number. Okay? No. I just keep. It is this number. Non-overlapping is not necessary. It's a metric, right? When we compare the topology, we are using this metric to compare. It's not necessarily saying the reality of what happens in the network. It's a metric. It's a quality. You can think about it as a performance metrics, right? When you divide this, right, you got a diversity ratio. That's this guy. Diversity ratio shows you how much better another topology, in this case it's the mesh topology, how much better, what is the growth rate in terms of path, right? In terms of non-overlapping path. Now, there's another thing you want to realize, okay? In the traditional, you are spending these just for routing, for passing, switching the packets. That's the purpose. Now, what if I reposition this, make them become another TAR? So you got a whole bunch of TAR here, additional one. Now, the bottom equation here is to say, well, now I got an equation for evaluating the maximum number of route path, right? Then I reposition, make these another TARs, right? Then I got almost twice number of TARs. If they are interconnecting as a mesh topology, right? How much additional or how many times of route paths do I get? That's what it says. When the n becomes 16, because it approaching number 2 very quickly, it's because it diminishing, approaching 2. That means if in today's data center GPU connecting, right? If we are willing to try, okay, to reposition, make the spine switch, save the effort, and make them the TAR. Let's say NVIDIA in the Selene supercomputer, right? They have a lot of these spine switches. What if we reposition it, make them another TAR, right? Then from the maximum number of non-overlapping paths point of view, you got twice number of paths than the Clos itself. That gives you an advantage of diminishing the condition because you are diminishing the condition of congestion of the network. Also, because you got twice number of paths, your cross-sectional bandwidth almost doubles. Why not give it a try, right? Our service is to let you try before you do a mass deployment. Think about it. Now, here we talk about Dragonfly. This is a very simple Dragonfly. It gives you the node count, and I'm going to the next slide. I'm going to give you all the goodies, right? The numbers looks very good. But right now we are looking at a very, very simple one, right? And what you see right now is you can think about this is a cluster, all right? And each cluster, the TAR switch allocate one link to connect to another cluster. That's how they look. What if you're allocating 2 links? Then you are double the amount of the other cluster you are connecting. You're growing the network. If you do that, the node count is become this equation now. Becomes this. Now, what we want to do even better, okay, if you really want to scale to supporting 500,000 GPU, that sort of thing, or even over 1 million GPU, then you are going to do more than just doubling. Okay, you can think about this. If you are deploying 128 node of cluster, why not? That node is called N. Why not alpha N? Alpha is less than 1. Meaning you are using a portion of the cluster size, right? Cluster is 128. If alpha is 0.5, you are using half each of the clocks, each of the TAR, the switches, allocating 128 times the 0.5, right? You're allocating 64 links to connect to the other clusters. Therefore, you're growing in the growth rate will be the equation underneath. You're growing very fast. How fast? Now, look carefully. Each of the switches or the TAR, right, are spending 2 links to connect rather than 1 link. So you're growing the network, and you're going to interconnecting them in a mesh fashion because it has all the characteristics we previously mentioned, okay? Now, this is the slides may surprises you because a lot of people say, oh, you are spending a lot of links, right? Now, this is saying in principle, okay? This is not what you really want to do, spending billions of links, right, fibers. This is in principle how this Dragonfly can scale. If you scale in the way the previous slides mentioned. You have a control, the alpha N, what alpha N should be. You can make the alpha very small, right? But this one, I make alpha equal 0.5, make it very big so that when N equal 4, I have exact picture on the left side for you to double check, right? To double check whether the number is correct or not. Now, if you believe or using spreadsheet to repeat these numbers, right, you can find out, I can tell you right now if you're using, let's say, Broadcom Tomahawk 4, even Tomahawk 4 can scale very big, or Tomahawk 5, then you can really, in the N can be either 96 or 128. Sometimes if you want to really push, it's 192. Then you got this many, you got over 1 million or close to 1 million number of switches, node. Even though each switch connect to a GPU, you got over 1 million GPU to connect to. Now in here, we are not talking about 1.6 T kind of per pole. We don't need to scale bandwidth per link wise, okay. I'm just using 100 gig. I'm sorry, it's the common switch you can purchase right now, right? It's 400, but if you do the pole breaking, it brings out 100 gig. I'm using 100 gig per link, and you can scale this much. Now, you got a very crazy number. The global path bandwidth are the paths, are the links linking the clusters, okay? And you got a very big cross-sectional bandwidth on the global path side, meaning you can make it equivalent to bisectional bandwidth in a cross topology. Now, for any reason, you may need such big bandwidth. You may not, but sometimes if you say, I want to grow my GPU, right, cluster size to a very big one, then you will need a lot of cross-sectional bandwidth. This will give you. Now, as for now, right, we are limiting by many things because we say we want to commercialize several technology, right, something, right. In the current BGP, even in the commercial side, the black box side, right, their implementation of BGP, they don't have that much number of VRF. Well, I just asked the ChatGPT 3.5, right, which vendor might have a lot more VRF, right? I think the number given back to me is about 1,000, and previously I saw it's about 256 VRF on the black box side. I think on the open source, the Sonic side, I don't know the actual number, but I think it's quite limited because we are not using VRF the way I'm using right now. We are limited by VRF today, and we are limited by route table size, perhaps, on some of the implementation. We are limited by the SAI, right? Because SAI configures your table size, limits you. And we are limited by, because some of the open source box, not every port, okay, can do the port breaking. So we are limited by the number of port breaking, impose a limit to the network size, okay. But however, all these are implementation issues. We can push it. As for now, upon customer's objective, based on your strategic routing, right, we can make alpha n equal to 1 or 2, probably that is the sweet spot. So any questions? Are we good in terms of time? How much time we left for? Oh, I have time. So I'm running too fast, right? Want to hear, let's say, want to talk more business or maybe business engagement? Yes, right. How much time? Can you read? 2 to 3 minutes. Business, right? I have a website set up, right? I can walk out, right? We can exchange, and you can also study in your company. I have a website, www.claruspon.com.
Sorry, when I said business, I wondered, for example, how this compares to all sorts of other industry initiatives, and what traction have you got? What response have you got to this idea with companies? There's all sorts of companies doing switching for very large GPU clusters. Mm-hmm. So I'm just interested in if you've started to talk to people, what sort of response have you got to this?
For instance, Sonic AI working group, I'm interested, and they are interested too, right? I spoke about this idea in the last year OCP. Microsoft, a lot of people stopping by, exchange, right? I need to submit some papers or some documents, right, for them to take a look. Microsoft stopped by. I think Google stopped by. Also, the IETF guy, chairman, stopped by. Right now, I need to make a business case, means people willing to pay for it, right? If it is indeed very good. Now, I just want to remind you your pain point, right? That's what I am asking. Are you still suffering on your Clos network? Are you still suffering making it a compute network? All right? Are you suffering from scaling up beyond 25,000 GPUs? are you suffering? I think you're definitely suffering, right, on interconnecting AI data centers, forming a data center clusters. Now, I didn't go to the WAN or the carrier network side because they are using the technology most likely is different, right? Carrier Ethernet or segment routing, that sort of thing, IPv6, right? Then a lot of things will take a lot of effort to get it over. Now, this is Ethernet-based, open source, community-driven, right? I am going to Sonnet AI, right? Now, you have to see, do you still have that pain point, the pain area? Now, this will give you at least the second thought. What's the root of the problem? Now, think about this. ECMP, the hashing function, right, in the cross topology, it has a limited, it just have that much of path to ECMP into. Sometimes the hashing function isn't good enough, right? It's a random generator, right? It isn't good enough, right? And as I point out, your route path, meaning the actual routing table build guiding the path to go to the route path, you don't have flexibility. Means you cannot take a shortcut. It's just a two hop, right? You are tied to your topology. It creates a lot of pain. Does your pain come from that if you see it this way? Now, in another, means you don't even have a chance to go to 3 hop or 1 hop in the cross topology. You are restricted by the topology. If you see the congestion, now what do? Because there's no alternative path, right? You do the congestion control, slowing down your source. What if you don't want to slow it down? Now, in a different topology, now you have a choice because the choice is defined by you, narrow down to routing policy. You can define it, and as a service, right, I help you to define it. I think there's a lot of things you want to try or engage us to see a demo, right? If you just think about this, right, it's starting to make sense. But you are thinking about how do you do it? Is this something other vendor, as you said, right? How do other vendors seeing it? This is the first presentation I make publicly. They are starting to see it. This is the first time, just a few days ago, my website is up and running. So they don't have time to respond it yet. But as I recall, in the last OCP, they stopped by my booth. I did a demo to them. They need some solid documentation to circulate in the corporation, right? They need some time to digest. Now they got all the material here, and 1 minute. Any questions? Now, if you want to engage to be convinced, right? I have an emulation environment. I also have a real machine environment as a stepping stone for engaging business. You definitely want to try. And the slides are there. You want to download and give a thought to see how it will reduce your pain on building these larger GPU, right? Relocating the spine, make them the TAR is the ROI thing, right? Even though in a smaller network, you can do so. Now, we are a commercial company, and we are also doing open source. We're doing 2 stream, right? I think that's it. Any questions? No? All right, thank you.